Hello and welcome to Postgres FM, a weekly show about all things PostgreSQL. I'm Michael, founder of PG Mustard, and this is my co-host Nikolai, founder of Postgres AI. Hey Nikolai, what are we going to talk about today?
Hi Michael, let's talk about checkpoint tuning, right?
Yes, so right ahead login general, right? WoW configuration. We had a really good request for this topic from one of our listeners, so shout out.
Right. So not only checkpoint tuning, but checkpoint tuning is a part of it.
Mm-hmm. Yes, absolutely.
WoW configuration.
Thank you to Chelsea for this one.
Thank you. Very interconnected topics. We should think about them both. WoW configuration and checkpoint tuning, they come together.
Yeah, should we go through them one at a time in terms of, what are checkpoints? Should we start there, or what is what is WoW?
Right. So what are checkpoints? Checkpoints. To talk about checkpoints, we need to talk about WAL first. Write ahead log, and write ahead log is like the basic, absolutely fundamental concept of any database system, not only relational, which says that first data is recorded to different place to some additional some kind of binary log or like write ahead log, and only then it's changed in memory in data pages, and this allows us to build recovery system. This allows us to survive unexpected restarts, failures, various bugs, and so on. And in Postgres, this also allows us to have physical replication because it's built on top of recovery subsystem. So if you think that you change some row in a table, first this change is recorded into write-ahead log, and only when we know that this change is recorded reliably in WAL, it's already on disk, only then you can see committed. The user can see commit, and the actual change in data, it still can be only in memory, not flashed into disk yet, right? So basically, we record twice. We record to write-ahead log the change, and we change the data in place where it's stored permanently. But this flashing to disk in the second case, it's not occurred synchronously. So we can see commit, but the data file, the table, the index files, they are not yet in actual state on disk. And the checkpoint, it's the process of writing so-called dirty blocks, dirty buffers, to disk. So dirty in this context means changed but not yet saved on disk. So it's if it's already saved, it's called clean buffer. If it's not yet saved, it's called dirty buffer. And when we have dirty buffers, it means that we changed a lot. We already reflected these changes in WAL. It's like the rule number 1, write ahead log. But it's not yet saved on disk. And when checkpoint happens, all dirty buffers are saved. And it means that next time we will need to start, for example, after some crash, power loss, anything, we will need, we don't care about previous changes because they are already reflected on disk, right?
Yeah, so we only have to worry about things since the last checkpoint.
Right,
and I guess that'll come up.
Them. Right.
Yeah, and just before we move on from the basics, because I had to read up a bit about this, the main reason we need this is to prevent data loss on recovery. So it's the idea of the dual system, the idea of having this is to is the D in ACID, I believe, the durability side, so preventing data loss.
Right, ACID is like the core concept of database system. It should be like if it says data committed, it never can lose it. Otherwise, it's a bad system. So write-ahead log exactly allows us to have it. And without checkpoint, we would need to keep a lot of changes and replay a lot of changes, and startup time after any crash would be very long. right? And so checkpoints happen all the time. They happen kind of on schedule. They also can happen during, for example, when we need to shut down the server or restart it. There is so-called mandatory shutdown checkpoint. So Postgres doesn't report that shutdown completed until this shutdown checkpoint finishes. Right, so it's also important to understand, and that's why sometimes we can see that shutdown takes some significant time because we have a lot of dirty buffers and we need to save them first.
Yeah. On this topic, I saw a good recommendation. I think it was from you actually around Postgres upgrades and the idea of taking a checkpoint, triggering a checkpoint manually to
right because
reduce the time needed.
During shutdown checkpoint, Postgres doesn't respond to new queries anymore. It says shutting down, so come later, right? But if we run manual checkpoint, a SQL command checkpoint, it can be in parallel. So we save a lot of dirty buffers ourselves, like just running select in terminal, in pSQL, for example. And then when shutdown checkpoint happens, it's already fast because there's very low number of dirty buffers, right?
Yeah.
So
yeah.
It's always recommended when we need to restart server, for example, for minor upgrade, or we need, for example, to perform switchover. This like not manual, it can be automated, of course, but additional checkpoint. I would say implicit. Explicit checkpoint should be there because after it will implicit checkpoint shutdown checkpoint will happen. So we need to help it to be shorter, faster.
Yeah.
Right.
So you already mentioned a couple of uses for the write-ahead log. One's recovery on crash. One is replication. I believe point-in-time recovery is another one. So tools like PG Backrest make use of it, I believe. Right.
Well, it's a different topic, but of course, right. If we perform if we store full copies of PG data, by the way, they never are in consistent state. If you copy PG data on live server, it's not consistent. So you need a bunch of walls to be able to reach consistent point, always. But you also can store the whole stream of walls additionally. And if this allows you to take some so-called base backup, PG data, corresponding to some point in time. And then you can replay additional walls and reach new point in time, and it can be arbitrary. So if you have continuous, if you store continuous stream of walls in your archive, you can choose any time you want. The only problem usually is if your database is big, quite big, the initial copying PG data initially takes time, and roughly like very, very rough rule is 1 terabyte per hour, but can be slower, can be faster, but very rough rule. So if you have 10 terabyte database, should be prepared for 5 or 10 or 15 hours of initial copy. And I wonder why people don't use often cloud snapshots for that, to speed it up. Right? It would make sense completely. But I know sometimes they are not reliable, cloud snapshots in Amazon and Google. Like, there are issues with them sometimes. Also, making them takes time, but we could do it on replica. It's like I put us to a different field. Let's postpone discussion of backups and other things. But you're right. Point-in-time recovery is another area of application of WAL. But the primary goal is to allow us to recover from unexpected shutdown or power loss or anything. So it's like in games, right?
Sorry, I lost you briefly then.
Yeah, I see. My internet connection and Californian internet providers are terrible. I complain a lot. I'm still waiting for my Starlink. Yeah, sorry. I see packet losses. Let me listen to you then. So. Yeah,
Well,
it's
yeah, so
improving. It's
I'd be,
improving.
I think it's getting better. I would love to hear a bit more. So I think like a lot of different parameters. So we have a lot of parameters for tuning these things. We have a lot of parameters for controlling, how fast, these things happen, how much has to happen before they, kick in. There's a few settings that it seems like we really shouldn't touch pretty much ever as well. And I was keen to, but it also seems that especially on high write workloads, there is some really big wins we can get by changing some of the default parameters.
Defaults are not good enough for you usually, right?
Okay. Is that generally true? Or like if I have a read heavy application and not a ton of writes, am I likely to, how would I know if I'm hitting problems? What are the first telltale signs?
Well, that's a good question. Usually, it's good to evaluate the distance between two daily backups, for example. And you can even, in SQL, you can even take two LSNs. Usually when backup is taken, LSN, logical sequence number, log sequence number. So it's like position in wall. It's always sequential. It has some specific structure. There are a few articles. We will attach articles explaining how to read LSN and how to split it how to understand the structure. So if you take two LSNs and convert them to PG underscore LSN data type in Postgres, you can subtract one from another, and the difference will be in bytes. So this difference, and then you can run PG size pretty size. And you can see the difference in megabytes, gigabytes, actually gigabytes actually, but Postgres doesn't use this notation. So you can understand how much WAL you generate during a day, right? If this size is quite small, like gigabytes or 10 gigabytes, it's quite small. Probably you don't need specific checkpoint and WAL tuning at all. But if you have 1 terabyte generated per day, it's quite a lot, and I'm sure you need to go away from defaults, and you will have better performance, better everything. For example, WAL compression is not enabled by default, right? And
I missed that one. That's great.
Yeah, but I'm going to check if it's enabled in recent versions, because Postgres defaults are improving, but still they are lagging. If you have heavily loaded systems, you definitely want to tune it. So if you have Postgres 13, for example, WAL compression is disabled by default. Let's talk about what is written in WALs. Oh, first of all, just simplify the explanation people usually use about checkpoints. It's like in games. You want to save your progress, right? And if something bad happens, you will repeat fewer steps, right? So it's very simple analogy. Yeah, it's still in Postgres 14, it's still not enabled, WAL compression. Yeah, in Postgres 15, it's still not enabled. And this is, I think, should be enabled in most setups. I'm almost sure on RDS it's enabled. So, and if you can, for example, do checkpoints very rarely, once per week, very not frequent, frequency is very low, right? Once per week, it's insanely low. But in this case, there are high chances that if crash happens, you will need to wait a lot while Postgres replays many WALs, right? A lot to do in terms of redo. And during this period, you will be down. Your system is down, so not good. That's why, logically, I would say it's good to have checkpoints more often, right?
It seems like it seems like a Goldilocks problem, right? Too often, and you have a lot of overhead, but too infrequent, and it will take a long time to recover.
Yeah, there is straightforward trade-off. There is trade-off here, and there are two kinds of overhead. We will talk about it in a second. But to understand where overhead comes from, in spite of dirty buffers, let's talk about what is written to wall. By default, full page writes are enabled, right? And what is full page write? It's if you change anything in some table, in some row, it may be a very small change. Postgres writes whole page fully to write-ahead log. Why? Because there is a difference. Buffer is usually 8 kilobyte size, 8 kibibyte size. But file system probably uses block size 4 kibibytes, and you don't want to have partial write during writing to disk reported as success, but you wrote only one half of it. So that's why full page write is needed. And by the way, first Postgres first talks about Aurora from Grant McAllister, if I'm not mistaken. They are very well explained. We will find links to YouTube and probably a slide deck. They explain very well this problem about full page writes and this big overhead. So when first change in the page occurs, first time it's written after checkpoint, it's full page write. If you change it once again, only small delta is written, right? So it's not full page write. But only until the next checkpoint. If checkpoint happened, all changes are initially again full page writes. If checkpoints are very frequent, we have a lot of full page writes. If checkpoints are not frequent, we very often we have repetitive changes of the same page. So we changed it. We, for example, inserted something. We insert once again into the same page. It's a new change. Again and again, we update something. We have had update heap only tuple update. So we change it the same page. And this means we touch the same page, we write to it multiple times. In this case, if I'm saying not only the amount of writes, the number of writes matters, also the nature of writes matters. If you have hot updates touching the same page many times, you will benefit from rare checkpoints a lot, because only one full page write will happen after checkpoint, and then you benefit having very light. You write a little bit to the write-ahead log every subsequent change until next checkpoint, of course.
Yeah, that's super interesting, and I think also it explains why people. So there's some people I've seen. I suspect this is a very bad idea, but turning off full page writes in order to increase throughput. But it feels like a very risky thing to do, and I feel like we're going to cover quite a few better ways.
Some systems can afford it. But you need to understand what your file system is, your disks, and like what settings they use. And in some cases, it's possible, but it's quite dangerous. You should understand all risks and be 100% sure that it's possible in your system. But usually we don't go this way. Usually we use ext4 with 4K block size and so on, and we want full page writes enabled. So back to compression. Compression is applied only to full page writes.
Okay. Interesting.
So we don't compress, as I understand, Postgres doesn't compress these small changes. It compresses only these, like, first time we change something in a page, we record this page fully, and we can compress it. And compression is not enabled by default. And if you enable it, you can see huge benefit in terms of how much wall you write. Why we care about volume here? Because if we have write-heavy system, of course, writing a lot additionally to wall, it's additional overhead on disk. If you have 10 replicas, sometimes people have it. all replicas need to receive this data. They work physical replication, logical as well. It works through wall, through write-ahead log. So if we write a lot, we need to send over network a lot. We want wall compression enabled to compress all full page writes. And we want checkpoints to happen rarely, to have fewer full page writes as well. So this, like, obviously I would tune max wall size and checkpoint timeout to have very, very not frequent checkpoints. But in this case, if they are not frequent, again, startup time after crash, also failover, for example, the timing of these procedures will be very, very bad, long, minutes. I see various engineers struggling to understand why, for example, shutdown takes so long, why restart takes so long, and they become nervous, and at extreme cases they use kill -9. So sick kill, like Postgres survives because we have write-ahead log and we just redo. Yeah. But redo also takes a lot. They kill it. It's not acceptable. Only in rare cases we should do it. It's like last resort. We should not do it. But after read, Postgres starts and startup takes also many minutes. They're still nervous. It's not a good situation. That's why people need to understand like how much wall needed to be written and distance between checkpoints.
Yeah, let's go back to a couple of those ones you mentioned. So my understanding is that checkpoint timeout is a maximum time between checkpoints, and that's default quite low, is 5 minutes.
Yeah, it's very low, very low.
So what would be a sensible starting point for most people in terms of increasing that?
Yeah, so usually like the main metric here is how long you can afford being down in the bad case, in the case of an incident. This is the main number you need to understand. You need to talk with your business people and find some number like, okay, we can be down up to 2 minutes, for example, right? From there, you start thinking, okay, if we have this like requirement or SLO, service level objective, if we are SREs, right? So if we have 2 minutes, let's think, okay, if we have 2 minutes, during 2 minutes, how much we can replay? We can measure it with experiment. We can, for example, set checkpoint timeout and max wall size to very insanely big numbers. Then we can have a lot of writes happening, pgbench, for example. Then we can wait until new checkpoint, one checkpoint finishes, another is about to finish, and then we kill -9 our Postgres, crash it on purpose. And then we see recovery and just measure the speed of recovery, how many bytes of wall we can replay per second, per minute. And this gives us understanding of like how much wall we can afford to replay not to exceed 2 minutes of downtime, for example.
Yeah.
From this, we can start thinking, like this is very important to understand, recovery speed in terms of bytes per second, bytes per minute, or gigabytes per minute, anything here. From there, we can understand then we need to understand how many bytes of wall we produce when everything is normal. During quite busy hours, usually at night, for example, we have lower activity. At daytime, on working days, probably we have more activity, right? But usually we say, okay, we produce like, for example, 1 wall per second. It's quite good speed. Each wall means this file. There is also confusion in terms because as I remember, documentation says wall file is some abstract thing. It's like 2 gigabytes and wall segment is 16 megabytes. But if you go to pgwall directory, you will see each file will be 16 megabytes usually. As I remember, RDS tunes it and they have 64 megabytes per each wall. So I say
Interesting.
each wall is usually 16 megabytes. So 1 wall per second during normal, quite busy hours, it means we produce 16 megabytes per second of all data. Right? So, okay. And it means that, okay, what is our replay speed? What is our production speed? And from there we can understand during which time we generate that amount of wall data, which will give us 2 minutes of recovery time. Right?
Yes.
Quite complex, I understand.
Well, it feels like luckily we've got that second parameter in max wall size.
Well, no. Let's
go
pause. Yes, I'm talking about how to, like, in my opinion, how to understand what's the best, what's like normal checkpoint timeout for you, right?
Yes.
So in this case, we understand, okay, recovery time is this, production speed is this. So we can conclude that to have not more than 2 minutes of recovery time, we need to have we produce this number of wall data. So we will set checkpoint timeout probably like half an hour. This is like quite like maybe 15 minutes, 30 minutes. It depends, of course. Observing concrete system, we can like make some conclusion. Okay, we want 30 minutes, for example. But then we start distinguishing planned checkpoints and requested checkpoints. Right? Requested checkpoints is like Postgres has two logics. One logic is, okay, on schedule. When time comes, time to have checkpoint. Every 30 minutes, for example. By default, it's 5 minutes. I think it's quite too often. Right. Yeah. But then if there is another parameter called max wall size, and I think it's very, very important parameter to understand. It's our protection for the cases when we have elevated activity, right? And we want to have more frequent checkpoints because we want to be protected again from writing too much data to wall and have again longer wait. Again, the same logic. If we understand how much we produce, the speed of production, we can say, okay, the max wall size also roughly corresponds to. So checkpoint timeout and max wall size can be like correlate. Their tuning can be correlated here, right?
Yeah. So my understanding is it sounds like we should rely on checkpoint timeout for the majority of the time. That should be the thing that kicks off checkpoints. But if more than that amount of while is generated, more than the amount we're expected, we could set an amount in.
We should set it. Postgres.
We will.
Right,
yes.
Right.
Perfect.
So usually, like, and default is there very small, 1 gigabyte default. It's insanely small for modern workloads. Usually, like, I recommend to go up, sometimes up to 100 gigabytes, but we need to understand this recovery over trade-off, right? So we need to measure recovery and guarantee our business that we will not be down more than, for example, 2 minutes or 5 minutes, right?
Yeah.
But, right, max wall size protects us from the cases when we have more writes, and Postgres can decide to perform requested checkpoint. We see it in logs. By the way, logging of checkpoints we need enable always. As far as I remember, recently default was changed and logging is now enabled. I remember discussion in hackers mailing list. So log checkpoint should be enabled for all checkpoints. I'm 100% sure. This is what you want to understand. Its default was false. Default is disabled in Postgres 12, disabled in Postgres 14, but enabled in Postgres 15, which will be released very soon. So this is new change. In Postgres 15, log checkpoint is enabled, and I recommend enabling it for any Postgres. So I also saw some DBAs see that like 90% of all checkpoints are requested. They occur according to max wall size. This is a problem. No, it's not a problem. It's not a problem because requested checkpoint and timed checkpoint, right, like planned on schedule, they are the same actually. Like no big difference. But of course, like you want to be like in order. Everything should be in order. Of course, you want like it's just a sign that probably you need to reconsider settings, but it's not an urgency situation, right?
Yeah.
Well,
Sounds good. Go on.
there
Go
is
for it.
another checkpoint completion target we
Yes.
didn't mention, and by default it's 0.7 or
No, this
already-
changed. I looked this up. Until very recently, it was 0.5.
Oh,
which seemed
0.5
like it
is
was always.
terrible, I would say.
But
It's not what you
in
want.
14, yeah, but in 14 it was increased to 0.9.
Great, this is good number. So what is it? Since when you run manual checkpoint, explicit checkpoint, it goes full speed. So it writes dirty buffers to disk as fast as possible, and it produces some stress on disk. It's okay stress, but it's normally you want to be more gentle with your disk system, right? So that's why we spread it over time. And 0.9 checkpoint completion target means that between two checkpoints, 90% of time we want to spend writing, and 10% of time we are resting. Maybe you want even more, 99. I don't know, like 99% of time. So, and this is important because, like it's hard to understand the distance between checkpoints. It's quite tricky question. Logging will report something, but you can think about when checkpoint starts. This is like the beginning. So 10 minutes between them is like, or 15 minutes between them, or 30, it's fine. But what I wanted to deliver, this is very tricky. It bothered me a few years, actually. And only in the book of Igor Rogov, we already mentioned it, with PostgreSQL internals. Yeah. So I read it in Russian even earlier. Now it's published, both parts are published in English, it's very good. So I finally, so it explains everything in detail with links to source code, and finally I understood why, if we set maxwell size 1 gigabyte, the distance in bytes, measured in bytes, it can be like 300 something megabytes. So it's like 3 times smaller.
Go on. Why is that?
So explanation is interesting. I'm looking at it right now. So I knew it from practice. I just, like, when I saw, oh, you have default 1 gigabyte, you know that it means that the actual distance measured in bytes will be 300 megabytes. It's tiny, like, distance. It means that checkpoint will disturb your system constantly. And I even saw the case of very large company where people had some cleanup job on the background happening. And then before big event, marketing event, they disabled this job. And then a couple of months later, they realized that job is disabled, and some engineer, very experienced one, but not Postgres expert, he like said, okay, this job was not painful at all. It was working many years. So he went ahead and tried to delete 10 million rows using one delete and put system down for 10 minutes because they didn't have checkpoint tuning in place. So maxwell size was default 1 gigabyte. Actual distance was 300 megabytes. I will explain why. It means that when you produce a lot, you have checkpoints happening all the time. Boom, 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 boom. And a lot of full page writes. Boom, boom, boom. It's not compressed. And disks work quite good, like enterprise disks, but not NVMe, unfortunately. And their saturation happened and they went down for 10 minutes instead. Just one delete. I even had a talk, I did it in Russia some time ago, like just about this case, how delete can put your, one line of delete can put your Postgres down even before you worked very well and like critical system. But so checkpoint tuning is an important thing to have. So if you have 1 gigabyte until Postgres 11, it was, if you have checkpoint completion target close to 1, you should divide by 3. Since Postgres 11, you should divide by 2. So if you have 1 gigabyte maxwell size, actual distance will be half a gigabyte, roughly. If your checkpoint completion target is 0.9. Because Postgres needs everything since last checkpoint and also everything between previous one. and latest one, latest successful.
Oh, interesting.
And before Postgres 11, additional cycle was needed. So 2 successful cycles and a tail, right? Not the tail. This tail is before, not behind us. It's in front of us, right? So if checkpoint completion target is 0.9, like roughly 3 times, like 3 intervals needed.
Yeah,
That's why you
interesting.
need to raise Maxwell size anyway, right?
Yeah, that seems like almost everybody would want to increase that one. I've read like there's some other interesting ones that I'd be keen on your view on, and also actually I guess are people on cloud providers? You mentioned RDS a couple of times. Are they generally more protected from this because they've been tuned already? The other
Tuning
interesting
here
one I want to
means increasing Maxwell size, increase Maxwell size, but do it not blindly, understanding recovery time.
Yeah. The other ones, min-while side, for example, I've read that can increase write performance if you increase that number.
For my practice, I cannot say anything here. Like I didn't dive deeply enough to discuss this, but Maxwell size is my favorite topic.
Yeah, if you haven't had to worry about min-while size, then I can't imagine it's that important. So yeah, good to know. And yeah, the only other one I wanted to ask about is while we're on the topic.
Sorry, like it's so important. I just want to emphasize it.
Yes.
Like so, if we have very short distance in terms of Maxwell size, forced checkpoints, and we have unexpected or maybe expected, someone decided to do it, a lot of write activity happening. We can measure it with experiments, and what I found that thin clones is good to iterate, but we cannot use thin clones here because we need our disk and file system behave exactly the same as on production. So I found a good recipe how to have some workload which will not touch our physical layout of data. It's a transaction of massive delete, like delete 10 or 100 million rows, but cancel it in the beginning, rollback. Delete will write to Xmax. We discussed it a couple of months ago, probably.
Yeah.
It will write the transaction ID which deleted tuple. But if transaction got cancelled, this is virtually zero. Zero means this tuple is still alive. So we produce a lot of wall, produce a big stress on system, but then we say nothing changed. And we can do another experiment on the same system. It's perfect workload for a lab, right? So we can have a sequence of experiments with different Maxwell size and see the behavior of, and we can, using like IOTop or IOStat, we can use monitoring. I recommend using Nate Data because it has export button. You can export all graphs and you can see how disk I/O behave. And usually if you have 1 gigabyte Maxwell size, and disks are not very powerful, you will see plateau because it's saturated plateau, right? Then you double your Maxwell size, plateau again, double Maxwell. At some point you will see how, like, your system under such stress, it's already not plateau and IOTop shows when Maxwell size is small, IOTop shows if you order by write throughput, checkpointer will be number 1. It writes like 200, 300, 500 megs per second. Insane, like it writes. And why, like, also understand, I promised to explain 2 reasons of overhead. One, we already discussed, full page writes. If we just finished our checkpoint and we needed to start another because Maxwell size commands us to have them very frequent. It's like insane checkpointing. Like checkpointer went mad, right? So for example, I saw like every 15 seconds, boom, 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 because these deletes, like we require 300 megs. It's quite fast, right? So again, default settings. So full page writes is one type of overhead. So basically, also make your deletes not sequential. For example, you can have some index on some random column, and you can say, let's delete first 10 million rows ordered by this column, but it's random. So first tuple is first page, second tuple is page number 1000. So we jump between various pages. And this is the worst type, because we could benefit, like if they are sequential, probably all changes in one page will happen inside one checkpointing cycle. But if we jump between pages, we constantly produce a lot of full page writes, and we need to produce them once again because checkpoint just finished, right? This is the worst situation, and this happens. This is exactly what put that system down, that I explained. So second, I didn't realize, but it's quite obvious. Second overhead is quite obvious. If our page was dirty, it was checkpointed, now it's clean. Checkpoint, okay, we visit once again, it became dirty again. We need to write it again. If two writes would be inside one checkpointing cycle, we would produce only one write. Right? But if we visited 2 times of our visits happened in different checkpoint cycles, we need to perform 2 disk writes.
So it's more I/O.
Right. So sequential delete is not that bad. Random delete, according to some index, can be very bad. Right?
Well, that's a good point. So as well as all the
sorry, so much pain. I spent some months exploring it, and we made very good, like I would say, enterprise scale experiments. And I can take any system and show exactly how recovery will behave, how exactly you need to tune. I can like show graphs. It's quite expensive in terms of time and probably money research of system, but I think big systems need it. They need to understand their workload, their system, and understand what will happen. So this random delete, I say this, like I named it double, how to say, like double unfortunate. You can be unfortunate because you crashed, and you can double, like you unfortunate twice because you crashed during some random intensive writes. Right? So in this case, you definitely want to understand your Maxwell size and checkpoint timeout, and you want your disk IO graph not to have plateau, but be like spiky. And this is a sign that you have some room for other writes, right? This is like our research shows, like, okay, at 16 gigabytes or 32 gigabytes, we already don't have plateau. So this is our like desired setting for Maxwell size, maybe 100 gigabytes even. Divided by 2, like we need to understand since positive. But and then we say, okay, but in this case, recovery time can be at normal time it will be this. At bad times when somebody is writing randomly a lot, it can be this, like 10 minutes. Can you afford it, or it's not good here? So you see how much like I had in the past with Maxwell size especially.
This is great, and I hope people are encouraged to go and you can easily check this, by the way, can't you? Just with all Postgres parameters, you can just use show Maxwell size. If you get 1 gigabyte back, maybe time to have a look at that. Same with checkpoint timeout. So show checkpoint timeout, check out that if it comes back 5 minutes, or it might say 300 seconds. Again, another one to look at.
Right. So
anything else?
There are other things, but let's stop at this point because we are out of time. Definitely here already. I apologize for too many details in this case.
I don't think that's the kind of feedback. If anybody thinks we did do too many details, let me know. But I don't think that's going to be the
right. I want to like advertise Nate Data here, because if you do some experiments and you take like same virtual machine, same settings, everything as production, you do this very unfortunate massive delete rollback, and you check with various settings, do install Nate Data and export all dashboard with all disk IO and everything to file, and then you can compare. You can open in browser several files,
snapshots,
and see exactly the difference in behavior for different settings. It's so convenient.
Yeah,
and you can store
those
artifacts long term.
Yeah, I enjoyed when you showed me that. I also wanted to advertise a few things. There's a couple of great websites for checking out parameters if you want to see like what they mean. Obviously the Postgres documentation's great, but there's also PostgreSQLCode.nf or PostgreSQLConf by Ongress that I'll link up,
Right.
and PGpedia as well. I find great for this kind of thing. They have a section on this that I found useful, so I'll share those as well.
Right. But like I suppose if you have heavily loaded LTP system, you probably will set checkpoint timeout to 15 or 30 minutes and maximum size to something like 32 gigabytes at least, maybe more. But better to go full fledged to conduct full fledged research and make decisions based on your requirements from business. Right.
Yeah.
Good.
Thanks so much, Nikolai. Thanks everyone.
Thank you, everyone. Yes, share is important, most important probably. And if you, by the way, I have special request to our listeners today. If you have a iOS device, please go to Apple Podcasts and like us, please, and write some review. We would appreciate it a lot.
I don't know if you saw, but we got a nice one already, so thank you to that person.
Good. Thank you, Michael.
Cheers, everyone.
Bye.
Bye now.